The broadcast is now starting. All attendees are in listen-only mode.
Well, hi, welcome to Coffee with Caleffi. Thanks for joining us today. Our presenter today, Kevin Freidt, is our Director of Product Management, and pound for pound, probably one of the best product management folks you'll run into out there. And he's going out on the road a bit these days, so hopefully you'll have a chance to meet him someday. And he's put together a great webinar. He puts a lot of time and effort into this, and I think it'll show as we go through it. And I've noticed I go to webinars, and I've done a lot of webinars myself, and they're kind of like a steer's horn. So you get a few good points with a lot of bull in between, but that's not going to be the case today with Kevin. So hopefully you'll enjoy this and let us know what you think. And the idronics, that's what we're up to. Issue number 23 is on the street. If you were getting these and they stop coming, just go and sign up again. Make sure these keep coming to you, because there's a lifetime of information in every one of these issues. So they're available. As you can see down at the bottom, there's our website. We can go and get the PDF copies of those also and keep them on your Dropbox or something like that, so the folks out in the field can use those. We're on a job site. And what we want to from you folks, if you could, is input on some other topics. Here's the topics that we're going to be, or the issues that kind of go with the topic that Kevin's going to be covering today. But we're always looking for more, topics to cover in the future. So let us know if there's something on your mind, and we'll work on that. So I think that might be all the housekeeping. Yeah, take it away, Kevin. Thanks.
Thanks, Bob. Appreciate it. Can you hear me?
Yep, sounds great.
All right, let's talk about today's topics. We'll discuss differences in designs, performance, accuracy, things like proper piping, flow rates. We'll look at some specifications and requirements that are different from thermostatic to electronic master valves. We'll talk about recirculation and balancing. That's a really interesting and information-packed section of the PowerPoint. And we'll touch on service and maintenance. And then lastly, we want to talk about thermal disinfection, raising the temperature to kill Legionella bacteria. That's near the end of the presentation. So, all right, so at a high level, 50,000 feet, here are some things that you might think of when you think of what are the differences, what are the main differences between thermostatic and electronic valves. What comes to mind here is, first of all, cost. In general, a thermostatic valve is going to be less. That might not always be true, but in general, that will hold true. Ease of installation and familiarity. Lots of these are installed out there, like approaching 1 million, right, Bob? And people are very familiar with thermostatic valves, so that's a simple one. Ability to handle scale. This is an interesting topic. An electronic valve gets the nod there because there are some models out there that can actually do a periodic sweep or a rotation of the valve seat to flush away scale, and we'll touch on that too. Min to max flow range. In general, an electronic valve can handle maybe a lower min and a higher max, and we'll look at that too. And we'll talk about recirculation temperature creep. This comes up a lot. We get a lot of questions about creep. What is it? How do we prevent it? And then we'll talk about the added functionality, alarming, remote access, and electronic valves get that nod as well. So before we get into the meat and potatoes, we actually have a poll question here. We'd really like it if everyone could answer this poll question. For plumbing applications, have you ever specified or installed thermostatic mixing valves, electronic mixing valves, both, or neither yet? So I'll pause for a few minutes and let everybody enter their vote.
Yeah, we'll run this for about 30 seconds, but we're just trying to get a feel for what's being used out there and how much traction these new EMV electronic mixing valves are getting in the market. That's be good information for us to have, so we make sure we're on the right page as we develop this product. So there we go. Thermostatic mixing valves at 47%. EMV's electronic mixing valves only 2%. Both 39% and neither at 13%, Kevin.
Yeah, that is interesting. Thanks everybody for doing that. Let's get into it. So the first thing we need to do is to define what is a master mixing valve, so we all know what we're talking about here. So it is a point of distribution valve. So if you look at this schematic here, this particular schematic has an electronic master mixing valve. So this is at the point of distribution, which means it's located near the hot water supply. These valves are governed primarily by a standard called ASSE 1017, and this is the cover of it, and a couple of quotes that describe what it is. Okay, this standard describes the point of distribution valve, and it also says there in that second bullet that you need to be providing also point of use or inline devices to prevent scald protection and do final control. The way I remember that is ASSE 1017 comes before 1070, and those point of use valves are 1070. Let's take a look at just one slide to look at what is this standard. It's interesting. There's basically 3 tests in this standard, and the first one is a conditioning test. So what they do is run the valve with 200-degree water and 125 psi for 6 hours. That's a kind of a torture test to begin with, just to make sure the valve doesn't leak or blow up or fail in any way. The main part of the test is a temperature control test, and so what they do is provide 140-degree hot supply. The cold supply water is whatever's available, and the inlets are set at 45 psi. That's the cold and hot inlets, and the outlet at 35. So there's a 10 psi difference across the valve, and they set it for 110 degrees set point. And then at that point, what they do is look at the actual water, and that table shown down below is the accuracy. So depending on the flow of the valve, they make sure that it's plus or minus 3 degrees if you're in that low flow range of 3 to 5 GPM. And you can be plus or minus 5 degrees in the middle range, and then plus or minus 7 degrees at the high range. So what they're really doing there is defining the accuracy that the valve needs to handle to pass the test. And then they reduce the flow by half and increase the hot water supply by 25 degrees. And the valve, during these changes, it has to be stable within those temperature variations there. And then it will pass the test, that part of the test. And lastly, they do a hydrostatic pressure test and pump it up to 500 psi for 5 minutes and make sure it doesn't blow up. So that's really the test that is used to qualify a point of distribution valve. All right, let's cut this thing open and see what's inside of a thermostatic master mixing valve. Now, this is pretty typical for any brand that's out there, but mainly there is this, I call it a thermostatic motor. So this gold part right here that the arrow is pointing to, that is a sealed element, and it's filled with a special wax compound that's heat sensitive. And what it does, it expands and contracts and causes this linear motion up and down right here. So as it heats up and expands, what it does is move this cylinder or this cartridge right in the middle of the body here up and down to then proportionally mix the hot and cold water coming in. So as the element is warm, it expands, and as it cools off, it contracts then to mix that water. Now, what's important for stable control is that you have well mixed water around that motor. If you have laminar flow or really low flow coming in through those ports, then you can envision that thermal motor might be hot on one side and cold on the other. And at very low flows, that can happen. And then the valve can be unstable. That element might not be sure what to do if it's hot on one side and cold on the other. So it's important to have enough velocity and well mixed water around that motor. And so that shaft is connected, like I said, to the cartridge, and it opens and closes those inlet ports in proportion. So as that stem moves up and down, it's opening and closing the cold ports pretty much proportionally. The set point, you can kind of see that here in the cutaway. It actually is connected to a spring that then changes the force that opposes that thermostatic motor movement, so that the temperature indications on the dial are calibrated to correspond to the movement of that thermal motor, and that's how it works to maintain temperature. One thing to note is that the mixing port never closes. Okay, it's always proportioning between the hot and the cold, and the mix is always the same opening. That's why it'll have a CV of, for example, 3. Now, I got a really interesting pre-submitted question here that applies to this. How would you pipe a 2-temperature system when you need hot water direct from the heater and tempered water to the fixtures? That's a really great question. So what this question is suppose we needed to pull some hot water off of this piping between the mixing valve and the heater for something like a commercial dishwasher or a washing machine. Can you do that? Answer is yes. But what that will do is it'll cause a pressure difference between the hot and the cold ports. So you have to be aware of that. And if you have much of a pressure difference between the hot and cold port, then the valve will struggle to control a stable mixed outlet. So that's when you have to use check valves. If you have something tied into actually either side, something tied in near the cold side or near the hot side, then you want to have those check valves in there, because you can imagine if you popped open a solenoid valve to feed a washing machine, it could actually draw cold water from that cold inlet through the valve and then backwards through that hot port, and it's just flow going the wrong way. And these valves are self-contained. They don't require any electricity. They are, just do what they do what they do, and that's pretty simple. Let's look at an electronic master mixing valve. Now, this sample is just a globe type valve. There are other types of valve, but the difference between an electronic and a thermostatic, in this one, it's linear also. So the stem right here moves up and down. That's similar to a thermostatic mixing valve. And inside, if we look at this cutaway, what we'll see up in the stem area or the bonnet of the valve are some packing seals. And the ones I'm familiar with have a Teflon type of what's called a V-ring, and they wipe the stem. And typically these stems are stainless steel. And so those packing seals keep the stem clean as it moves up and down. And this example here, if you look, there's 2 inlets. There's an A inlet on the left and a B inlet on the bottom. And there's 2 seats there. So that plug has a seat, mating surface on the bottom, and then another mating surface on the top. So as the stem moves up and down, again, it proportionally changes the flow for the 2 inlets to the outlet. Now, most, I don't know most, but a lot of globe valves have metal to metal seats. What that means is there's no soft seating surface in there. And now a metal to metal seat is going to have some amount of leakage, and we're going to talk about that in just a minute. Another kind of electronic master mixing valve or valve type is a rotary or a 3-way ball valve. Now here's a cutaway of the Caleffi Legio mix. So rather than being linear, it's rotary. So the stem rotates 90 degrees, and up in the stem area, typically you'll have O-rings. So as the stem rotates, it rotates within the O-ring seals. And that ball will rotate, I don't know if you can really see it here, but there are rings on the edges of the ball here, and that's where the seal is provided on a ball valve that's rotating. So both of these types, no matter what kind of electronic master mixing valve you have, they require some sort of proportional or floating control actuator. They have to modulate. So a proportional actuator would be a 0 to 10 volt or 2 to 10 volt, or perhaps a 4 to 20 milliamp proportional type signal, or a floating, which is a 3-wire drive one way, drive the other way signal. Those are all modulating, and to do mixed temperature control, you have to modulate. So that's the actuator. You also require a controller. Something needs to tell the actuator what to do, and that is, in this case, there's the controller for the Legio mix. And you have to have a sensor in the mixed outlet. So in this picture, you can see that sensor next to the gauge is screwed into the outlet adapter there, and that sensor is wired to the controller, which then tells the actuator what to do. Here's a flow chart or a diagram that I like to use. So in the mixed water is a temperature sensor. As the water temperature changes, that sensor will send a signal back to the controller, as an analog input, and within the controller is some type of a control algorithm. Now this might be a proportional integral or a PID, proportional integral derivative type of algorithm. But what that does is compares the set point that you've programmed in the control to the value coming back from the sensor, looks at the amount of error in that signal, and then decides what kind of a modulating signal to send out to the actuator, which then positions the valve, which then changes the mixed water temperature. So this is a closed loop control system, just a really basic look at how that works. Now in this picture too, notice this sensor right here. The Caleffi Legiomix product has a return sensor. Now this is used when we do thermal disinfection to kill Legionella. So I wanted to just point that out. That's not really typically required for doing normal mixed control. It does give you the value, but it's used in the control logic for thermal disinfection. Some of the differences in specifications, I mentioned earlier, the thermostatic valve is just standalone, doesn't require any electricity or electrician or anything like that. I want to talk about fail-safe or spring return. That question actually comes in quite a bit when we're talking about the electronic mixing valve. So the Caleffi product that you see on the right does not have a physical spring, so it's not spring return. It doesn't have a fail-safe mode when you remove power. Fail-safe is a term that I use if you have a supercapacitor or some other type of electronic technology in the actuator. You can do the same thing as a spring return does. It's just an electronic way to position the valve in the event of loss of power. How important is that in a master mixing valve? It's a good point of discussion. If you lose power in the building, your recirc pump's going to turn off, everything's going to turn off. And so then if you have water draw at a fixture, that valve is just going to be sitting in the last position. Is that bad? Don't know. It depends. Either way, we highly recommend using a UPS or an uninterruptible power supply on anything that's critical, such as an electronic master mixing valve. What about accuracy? I mentioned earlier in the discussion on ASSE 1017 that as long as you pass these temperature variations, then you're approved to ASSE 1017. So that's doable with a thermostatic or an electronic valve. It's not actually that difficult to maintain that kind of accuracy. Now accuracy, some folks will say that an electronic valve is more accurate. It certainly can be, and it can be faster depending on how you program it and whether you use the PID program or some other algorithm. You can actually change and control the speed of response. But really the accuracy depends a lot on the valve type, the mechanical side of the valve, the design, and in combination with the actuator and the controller. So all of them together will affect the accuracy. So really, just check the literature, the data sheet on the individual products that are out there for that accuracy. And of course, they're all going to say 3% or better because they have to pass ASSE 1017. What about the sensors? I mentioned that thermal motor, that integral wax element in a thermostatic valve, really basic. Now mixed electronic valves will use maybe a thermistor or an RTD or some other type of electronic sensing device. They're all going to have to meet the low lead laws for North America. ANSI NSF 372 is the one that governs products used in drinking water. So all the products that you are able to buy to do this are going to meet that law. One of the questions came in, what about sizing the valve? Is there a different approach or a different way to size a thermostatic valve compared to an electronic valve? And the answer is no. What you're really looking at is, the demand in the building. So you might use a table like this that discusses fixture units, or there's information in the Uniform Plumbing Code, or IAPMO has this water demand calculator. So whatever you currently use to size for the demand is good for either a thermostatic or an electronic, no different. What about a user interface? How do you look at a thermostatic valve? Well, you really just have the dial set point, right? So the man to valve interface is really just a physical dial, and you may or may not have a temperature gauge to provide you with feedback. That's all there is, of course, with a standalone thermostatic mixing valve. But electronically, everything opens up, right? The world is available to you. So there are a lot of products out there that have LED, LCD user interfaces. A lot of advantages to going with this. Okay, first of all, you can set an exact set point. You can set it for 120 if you want, and with a dial, you're getting as close as you think you can. There are a variety of configuration options, local and remote indication of temperatures and status and everything, just like any other electronic product. And of course, that gives you web access, integration to a building automation system. It's wide open. It really depends on the product that's available. Get into a little more technical detail here. Let's talk about close off. What I'm talking about here is the inlet ports, the hot and cold inlet ports. Most thermostatic valves are not designed to close off 100% on those two inlets, and that's not a problem. Some, what we'll call flow through is actually pretty normal. And if you're thinking about just regular mixed temperature control, it's really not an issue. The thermal element will move up and down and mix the water as it needs to maintain set point. Now that can become a problem, and we're going to discuss this in detail later when we're talking about recirculation and temperature creep. So we'll wait and get to that point. Another thing to note is that metal to metal seat globe valves will have some flow through. There's actually an ANSI standard that's called a leakage standard, and there's like class 1, class 2, class 3, class 4. Whenever you have a metal to metal seat, you're not going to get what's called a bubble tight close off. So that means that a globe valve that has a metal to metal seat could still allow temperature creep in a recirc system. Most ball valves, just by the nature of the ball and the seals, are what are referred to as bubble tight. So there's no flow through. What that means is that the hot port will close 100% and the cold port will close tight as well. So that means a couple of things. First of all, you eliminate creep, and we're going to get into that too. But something else to think about is if they can close off tight, then they can operate on less of a differential temperature from hot to mixed compared to a thermostatic valve. If you look at a spec sheet for a thermostatic valve, you might see something like minimum temperature difference between hot and mixed equals 18 degrees or 27 degrees. Okay, that's something that becomes less of a concern when you have a valve that will close off tight. What about capacity? A lot of people asked about capacity, so let's spend some time on this. The capacity of the valve depends on the type of the body and the design internally. So here's a table that shows just some references, 3 different pipe sizes, 1, 1.5, and 2 inch. A typical maximum CV for a thermostatic valve, you can see there 3 to 7, maybe 12, maybe 16 on a 2 inch. And when you go to the different types of valves, the flow capacity changes a lot. A spool or a cage type valve or a cartridge type valve, generally they're a little higher. You can see that these numbers are higher than the thermostatic. And a globe valve, 12 maybe for a CV on a 1 inch, maybe 30, and then 45 on a 2 inch. Those are, if you look across the industry, those are pretty typical maximum CVs. But the ball valve, look at that, the CV, the maximum CV for a ball valve is significantly higher. Now, why is that? Ball valve will have higher flow capacity because they have lower pressure drop. The larger effective area, through the internal side of the valve allows for more flow and lower pressure drop. So what that actually means is there could be cases where you could use one ball valve where you might need 2 of the other types of valves to meet a certain maximum GPM requirement. You know, if you're on the bubble there with the GPM maximum. Here's a graph for a typical thermostatic valve. This is actually the Caleffi 521. So what we want to talk about here is flow range for the thermostatic. The maximum flow that you're going to get through a thermostatic mixing valve is really based on what I refer to as a reasonable pressure drop. What does that mean? If you have too much flow through any restriction or too high of a pressure drop, no matter what it is, you're going to be looking at potential noise, maybe some cavitation, maybe some erosion. So what we suggest in our Caleffi products is to try and stay at a maximum of about 20 psid through a thermostatic mixing valve. Now you can go a little higher, and you can, you know, periodically, but what we're talking about is right up here in the graph. So if you go higher than that, you're just asking for problems. And if you go a little higher and get a little bit of noise, if you back down, okay, not a big deal. But this is a guideline, and this is what we recommend. The minimum flow on a valve like this is really based on the control stability. Remember, I mentioned earlier this whole issue of laminar flow and that you need a nice mixed turbulent water flow around the thermal motor to keep it stable. That's basically how we determine the minimum. And that really is determined in the lab by empirical testing. It really depends on the design of the valve internally. So there's that statement about, you know, well mixed water. And you need a differential between hot and mixed. I mentioned that earlier too. So a thermostatic mixing valve needs to have temperatures to work with, okay? It needs a good hot temperature that's significantly higher than your mixed outlet set point, and it needs the cold water to work well. So this valve right here, I mentioned the 20 psid maximum. Here we are right here at the top of the range. So in terms of what we recommend, this is pretty much the maximum, and that would correspond to around 15 GPM if you come down here on the x-axis. And this valve has been tested, and we know that it performs very well down at about 1 GPM minimum. So it will actually work lower than that, but we know that right in this range right here, or a 0.1 PSI pressure drop across our 521 series mixed cal, it works great. So this is the flow range of this valve that has a CV of 3. And there's the equation that we use to determine flow based on CV and pressure drop. So what if we need more than 1 to 15 GPM in a master mixing valve? Here's a product that we have that is we call a high-low thermostatic valve. And what it does, if you look down here, this is the 521 mixed cal right here. So there's a 3/4 inch mixed cal, the one we just looked at on the graph. That's this valve down here. Here's the big brother of that, the mixed cal plus. This is an 1.25 inch valve. And what we have here is these are piped in parallel, but right downstream of the big valve is a PRV. And when the capacity, the flow through this assembly starts to get up around the maximum range of this little valve, this pressure drops right here at the PRV will fall off and then open the port, so the big valve kicks in. So they work together in a staging kind of a relationship. And this assembly right here will deliver 1 GPM to 50 GPM. So remember, we looked at the valve by itself, it was 1 to 15. Now we're looking at 1 to 50 in this high-low assembly. So that's a very good approach. A lot of these out there, a lot of people build their own. We make this just like you see it here and ships in a box ready to go. What about the flow range for an electronic valve? Generally, the ranges are higher. So let's look at this graph here. The Caleffi valve that you see here in a 1 inch has a minimum of 3 and a maximum of 94. Here's the 1.25 inch, so 4.4 GPM to 107. Now these max flow ranges are based on that 20 PSI drop that I mentioned earlier. That applies to everything, and that's our recommendation. So you'll notice too that the minimums are a little bit higher. Well, Yeah, that's the nature of a modulating valve like this. Now, one thing to know though is that whenever you're using one of these valves, you're probably going to be looking at a recirculation system. So if you have a recirc pump in this commercial application, generally it will fulfill these minimums. So if your recirc pump is running 3 GPM, then essentially with this 1-inch valve, you have a minimum flow of 0 draw from the fixtures that will still be within the control range of the valve. The maximum flow, again, is going to follow that same rule. You know, like I mentioned, 20 PSID is a good rule of thumb, at least for our products. You'll see literature out there that says max differential 65 PSI, and that's just amazing, really. Who is going to put 65 PSID across a master mixing valve? That's kind of insane. The minimum flow will depend on the valve type and the valve design. Really, the literature is going to tell you. Any of those electronic master mixing valves out there will tell you what their minimums are. And that just is based on the capability of the valve to provide good rangeability from maximum to minimum flow. Switch gears a little bit. Let's talk about piping. When a mixing valve does not have tight close-off, so here's a schematic that shows a thermostatic mixing valve, and let's assume that this valve has a little bit of flow through on the hot port and the cold port. What can happen is you can get temperature creep. Let me tell you what that is. In any recirculating hot water distribution system, okay, there will be times when the circulator is operating and there's no water being drawn at the fixtures. So you can look at this as being a closed loop condition. If there's no draw, you cannot add additional cold water. What that means is you have to maintain that recirculating hot water temperature using just the return water, okay? And if you have a little bit of flow through on that hot port, then you can get creep. And what happens is if more heat is being added to that recirc loop than is being given up by the supply piping to the ambient air, then you get creep because you're adding more heat to the piping than you are removing from the piping. So if you think about that, if your piping is well insulated, which it should be, then the chance of creep is greater. If the piping is not well insulated and you have a lot of heat loss in that supply line from the valve out to the fixtures, you get a lot of heat loss to ambient, then maybe a little bit of flow through at the hot port will not cause creep. But that really all depends on what's going on in the installation. So what you have to do to prevent that is add this bypass valve right here, this little valve right here, number 1. This return valve is kind of optional, but what you have to do is put this valve in right here. And what that does is, oops, excuse me, let me go back. That throttles the amount of water that can go back to the tank. So what you do is you close this down almost all the way, and that really minimizes the amount of recirc water that can be added back into the tank, which then means that very little water will be coming out here and going into the hot port. So with the pump running, you tweak this down tighter and tighter and tighter until very little water is going back to this tank. Does it make sense, Bob? All right. Now let's say that mixing valve has tight close off. In other words, we have a master mixing valve here that does not have any leakage coming into the hot port right here. You don't need the bypass balancing valves. Why? All this recirc water that's coming back, none of it can go into the tank because none of it can come out of the tank. So in that case, the return water is coming back here, going back into the cold line, and then out here where the heat is transferred out to the ambient conditions and then back. So creep is eliminated when you have a valve that can close off tight. Let's talk about balancing. Very, very important. balancing is cannot be underestimated here. What we have is some pictures of different types of balancing valves. This is a manual balancing valve from Caleffi. This is a variable orifice type. Here is a fixed orifice type of balancing valve, manual. And here is the Caleffi quick setter, which is a very unique manual balancing valve that has a built-in flow meter. This product right here is a dynamic or an automatic balancing valve. It has a fixed GPM cartridge in here, so when you install that, it will maintain a fixed GPM value, even if your pressures fluctuate. And this is a thermal balancing valve right here, the Caleffi 116 series. So any of these balancing valves can be used successfully with either an electronic master mixing valve or a thermostatic master mixing valve. So let's talk about balancing a little bit. Here's a circuit that is not balanced. So you can see coming from the water heater, the riser that's the closest to the heater is going to get the most flow. The next one will get a little bit less, and then the one way out at the end is going to get very little flow, if any, because we don't have any balancing going on in this circuit. That's a big problem, especially if you're someone out here at the end of the line trying to get hot water. What if you put in a manual or an automatic balancing valve? What you do is you set the GPM for each of these risers to be the same. So a manual balancing valve or an automatic one will set the same flow rate. Now we're balanced, okay? What I want to talk about is a thermal balancing valve. It's a different animal, okay? It does not balance GPM. It's shown right here. This Caleffi thermal balancing valve, the thermosetter, uses temperature. So rather than looking at GPM numbers, we're looking at temperature numbers. So all you do is you set this dial to a specific temperature, and they modulate open and closed to vary the flow in each of the risers to maintain temperature. So it's a really interesting concept. So I want to spend just a little bit of time talking about that. Here's a cutaway of the Caleffi 116. So this gold colored element right here, it's the same kind of thing that you would see in a master mixing valve that's thermostatic. So it's a sealed wax element, expands and contracts. And as it expands and contracts, it opens and closes this seat right here. It's the only balancing valve that actually modulates flow in a riser. That's what's different about it. Here's a graphical representation of how it works. Let's say we had the dial right here tuned in at 140 degrees Fahrenheit. As that water cools off, let's say the hot water supply is depleted or you're doing a startup or something like that. If the water coming into the valve is lower than what you have set, the valve will modulate open. What does that do? That brings more hot water to that riser to then bring the temperature up, back up to set point. So these valves will generally work right in this region right here. They'll modulate open and modulate close to maintain temperature at that location. So very, very interesting concept. It eliminates balancing altogether, right? If you install this valve and you set the set point knob, there is no balancing. You just walk away. It will do what it needs to do to control temperature at that point. And I have a saying I like to use, it's a temperature solution for a temperature problem. So we're not having to use a differential pressure manometer and tweak and use charts or circular tools to set differential pressure that then corresponds to GPM, that then corresponds to temperature, right? Because that's what you're doing with a manual valve. And it doesn't rely on a fixed GPM. It just goes right to the point and controls temperature. What does that look like in a system? This is a nice graph. I like to use this. Here's some staged tankless water heaters. Let's say that during normal operation, these are set for 140 degrees. So they're delivering 140 degrees to the electronic master mixing valve. We have that set at 130, which is a good supply temperature. And that supply water is going out to the system where we have anti-scald valves, okay? Very important at all locations to have anti-scald valves if you are delivering water temperature anything north of 120 Fahrenheit. So then also in this schematic, we're showing the 116 series balancing valve. Where you install those is on this return pipe just before it joins back to this main return pipe trunk here. So this location is after all the fixtures when you're coming back on the way to the variable speed recirc. Why do we have a variable speed recirc pump here? Think about that for a minute. I mentioned that the 116 valves, the thermal balancing valves, modulate flow. That's different, right? They're not the same as the manual or automatic. So as these thermal valves open and close, what's that doing? It's changing the head loss in this return pipe. So if you put in a variable speed or a smart pump here and set that for a constant differential pressure, it works great with these thermal balancing valves, because as they control temperature, this pump will ramp up and ramp down to deliver the head pressure necessary to deliver the right temperature water out through the system. So you could call that a great marriage. Okay. We had another question that came in. What if I set my tankless water heaters to the temperature that I need at my fixtures? Do I still need a master mixing valve? Technically, no, right? So if we wanted to deliver 120 degrees out here, we could set these water heaters to, whatever, 125, and eventually just deliver that temperature directly out here. A couple of things to keep in mind if you do that. One is your return temperature. By the time it comes back in your recirc lines and gets back to your recirc pump, that water may be tepid. It may be at 100 or 95 degrees. That can be a problem, and I'm going to show you why on the next slide. So you're operating a low temperature system that can be susceptible to bacteria. Another reason you may or may not want to do that is if you set these to 120, that's all you have. So if you have any kind of industrial washing machine or a dishwasher, or if you have anything out there that wants to use really hot water, then you don't have the ability to do that. So great question. Thanks for that question. I talked about elevated temperatures. I want to just touch on controlling Legionella bacteria using elevated temperatures, or what we call thermal disinfection. Okay, I have a whole nother presentation on this, so we're not going to go into too much detail, but just briefly, Legionella bacteria, like shown in this picture here, is everywhere. It's in lakes and streams and even in the dirt. Now, it can actually get through the municipal water treatment as well. So it's very, very common, or can easily get into your plumbing system. Okay, so this stuff getting into your plumbing system will find a place. If the water is right here in this optimal growth area between, in this gold band here between like 68 and 118 or whatever that is, that bacteria, if it can hide in the biofilm or the scale or any corrosion layers, it will grow and proliferate in your plumbing system. So keep in mind this temperature range right here. So to kill that bacteria, there are two things you need to consider. First of all, you've got to get up into this kill range. You've got to get up above this point right here into the red zone or the kill zone. And you have to maintain that temperature for a period of time. So it's a time and temperature formula to kill Legionella bacteria. So why do I talk about all this? If we have a thermostatic mixing valve, you can set that on the tank and set your tank temperature for 140 using your aquastat or whatever is controlling your storage. And so this water is safe, right? This water is 140, so it's up in this red zone. You won't get any bacteria growth in this condition. But what happens when you deliver that water through the thermostatic mixing valve out into the system and back? It's very possible that then your temperatures are going to be down into this range here, which is undesirable. You want to stay out of that range all the time. So a thermostatic mixing valve can't protect the recirculation system because you can't elevate that temperature up above where you need to be to deliver the temperature water that is going to kill the bacteria. Now, with an electronic valve, you can do this. you can actually disinfect the whole recirculation system either by manual or an automated process. So most of the master mixing valves out there, the electronic ones on the market, have a button on the front or somewhere in the user interface that you can activate a shock. And what that shock will do is it'll tell the controller to set the tempered water set point up to 160 or so. And what you want to do is leave it up there for about a half hour. I know this says kills bacteria instantly, but you need to recirculate the whole system for like 30 minutes or so at those temperatures. And you need to monitor that return temperature. So the Caleffi Legionella product has that return sensor that we looked at earlier. It will look at that return temperature sensor and make sure that we're well up in this kill area for that half hour to make sure that the whole system gets sanitized. An electronic master mixing valve can interface with the hot water source. So maybe a contact output, for example, can tell the water heater to go to a higher temperature if you have a second aquastat, for example. And an output on the electronic control can make sure that the recirc pump is on. So whenever you go into this mode and you're doing a thermal disinfection, of course your recirc pump has to be running so you can verify that that's on. And if your controller has memory, it can log everything that's going on. So the Caleffi product has a 40-day first in, first out buffer that records everything all the time. So it will record all the temperatures, the supply and the return, any alarms that occur, any status changes, and gives the building owner or the building manager a complete history of what's going on. Those are important things to look for if you're going to employ this strategy. So how does that look now? Back to our system picture. So what we would do during this thermal disinfection is jack up our supply temperature to about 170, mix it down to about 160, send that very, very hot water out through the whole system, come back at 150. Now we are well within that kill zone for that half hour period or whatever you set it to make sure that all the bacteria is killed. And it will even kill the stuff that's hiding in the biofilm and the corrosion layer, because if we're at 150 degrees for a half hour, that whole pipe is going to get hot. So this is a very effective way to control Legionella is by using elevated temperatures. And you need that electronic master mixing valve to do that. So I talked about that thermal balancing valve and then elevated temperatures. Well, if your thermal balancing valve is sitting there at minimum position, how do you get enough water flow through the system to do that disinfection? The thermosetter has an optional second cartridge here. So this is another thermal element. If you send 155-degree water down the pipe, this element will pop open, and that's represented by this green curve right here. This is the bypass disinfection cycle using this second thermal motor. It has a real tight throttling range, so what it'll do as soon as it sees that temperature from 155 to 160, it opens up to a CV of 1.2. Now that's a nice big CV, so if all the balancing valves are opening up, then that will allow you to get really good flow through the recirc system and allow you to accomplish that disinfection cycle. There's another option too, and essentially in that second part of the body is a little zone valve, and it's actuated by a 24-volt spring return on-off actuator, 2 wires, so you can send 24 volts to all of your balancing valves and pop them open anytime you want to do a, to open up the valve to a CV of 1.2 so you can get a good flow through the system when you're doing a flush or a disinfection cycle. So I wanted to mention those as a kind of an added advantage to that thermal balancing valve if you're going to do thermal disinfection. How are we doing there, Bob? Mark, any questions so far?
Yeah, there's been quite a few coming. I don't know if Mark's been typing back responses I haven't seen, but if not, we'll grab some at the end. All good questions too. Great.
Well, we're doing good on time, so there will be questions at the end. I only have a few more slides and we'll have time for questions, so keep them coming.
Okay.
All right, so let's talk about service and maintenance, comparing thermostatic to electronic valves. We know that scale is a reality. Hard water is everywhere. It's tough on everything. It's tough on valves, it's tough on pipes. Just plan for it. This is something that it's important. So what you want to have as a building manager and owner is to have a regular inspection plan. It's a lot better if you install isolation valves. I know that's an initial cost, but we don't always see that. So that causes really headaches during service and maintenance. You know that scale remover, like this lime away stuff and CLR and vinegar and water, I know Bob is a big advocate of this. You can actually pull a valve out, drop it in a bucket of this solution and brush it off and rinse it off and put it back in service. So that's something to know. At least our valves are cleaned that way. Now look for a valve that has internals that are designed to resist this. Okay, if you have, I know the Caleffi mixed cal valve, the engineered polymers inside of there really resist scale buildup, and it's easily flushed away because it's really smooth. Look for a valve body with union connections. Anyone who's done any pipe fitting or plumbing will know that union connections are your friend. Union connections just allow you to quickly pull a body out and clean it and put it back in, and minimizes downtime. So that's a nice feature. And something to think about too, electronic assemblies that have the integrated controller. So if you have a master mixing valve and the controller and the user interface is attached directly to the valve, those can be expensive and difficult to service. And you might have to take them offline completely. So that's something to consider. One good thing about electronic valves is they can let the service people know what's going on. They can generate a service alarm if you have a sensor fault or a high temperature alarm. Of course, you can't get any of that with a thermostatic mixing valve. So that's a really big advantage for electronic valves, in the realm of service and maintenance. And something I didn't mention yet, but our valve, and I think one other product on the market has something that is a full cycle exercise. So it's an automatic, maybe in the middle of the night, where the valve goes fully open, fully closed, back to fully open. And what that does is it actually exercises the movement of the valve and seat, and it can clear debris and reduce service frequency because you're flushing away anything that might be, trying to cling to the seat and the plug or the ball of the valve. So that's a great feature to have. It helps with service and maintenance. A few other items to kind of sum it up and take away. I mentioned early on that thermostatic valves tend to be lower cost. Okay, we know that. They're easy to install. There's no wiring, no electricians. So that's why they're so popular. They've been around forever, and there's nothing wrong with thermostatic mixing valves if they work for you. Electronic systems with a full function user interface. What I'm talking about here is the push buttons for configuration and the display and the alarms or everything are right there on the wall mounted at the user interface, compared to a master mixing valve that you have to bring your laptop out there and plug in the laptop and then bring up your browser or your application. It's just really nice to have everything right there in the user interface that you can go to. Our product, the Caleffi Legiomix, actually has 11 languages in it, so you can select, everything from French to Spanish to it's a global product. So if you are working with customers in a global way, or if you're working up in, for example, Montreal, or down in a state where maybe the building manager would prefer Spanish, you can just set that. Really a great feature. A couple of other technical things. The seals in the Caleffi Legiomix are made of peroxide cured EPDM, and that's important because EPDM, when it's peroxide cured, then stands up to chloramines, and a lot of public water has chloramines in it. EPDM that's not peroxide cured will degrade quite rapidly compared to the peroxide cured seals. And if you are using a brass product, a lot of valves out there are either they're stainless or bronze or brass. If you buy a brass master mixing valve, it's better to get the DZR or dezinkification resistant alloy, and that stands up to aggressive water, because aggressive water can actually leach the zinc out of the brass, and it causes micro cracks and eventually the brass can actually fail if too much of that zinc is extracted out of the brass. So just to kind of sum it up here, as you can tell, we believe that an electronic master mixing valve coupled with a variable speed or a smart recirc pump, set that pump to constant differential pressure and put in a thermostatic balancing valve, and that will give you the ultimate in a modern, for a modern domestic hot water control system. So that's where all of this was leading. A lot of advantages to electronic master mixing valves. Wanted to show you this picture. This is a great shot of a retrofit project, and the first thing that kind of jumps out at you here is how small that Legionella valve is compared to where there was a large thermostatic mixing valve assembly. The second thing is there are some balancing valves there. You'll see 3 of those. Remember we talked about thermostatic valve having some flow through on the hot port, and we needed those little balancing valves in there to prevent creep. This contractor that did the retrofit, he just left them in there. They're not required for use with this valve. He just left them in there because it's easier to pipe. So it's a great picture for those 2 reasons, and it shows some really nice work. So let's see. So those valves were left full open. They're not functional. They don't do anything. The Caleffi product there has a little integral temperature gauge, so you can see the mixed sensor right behind the gauge.
We've had some comments and questions coming in concerning applications of thermostatic mixing valves, and the questions were along the lines: does the Caleffi thermostatic mixing valve, is it a problem if they go through periods of no use in terms of functioning properly? And one of the writers had indicated that they see in like college dormitories where, say, if there's no demand for the summer, that afterwards the mixing valve, not necessarily Caleffi, wasn't working correctly. And this photograph is a good point to make about thermostatic mixing valves. Thermostatic mixing valves, if you have any type of hard water situation, even 2-3 grains, they naturally wipe any calcium buildup as they exercise, as they modulate. As there's demand, they basically go up and down, up and down. But with really hard water, that can end up becoming, the problem. And most thermostatic mixing valves in hard water applications will actually, that's the failure mode that gets scaled up. But it's especially pronounced in cases where you have a little bit of hard water, but periods of no demand. And because they're not exercising, they're not moving. And maybe the hot water heater is still left on in that dormitory, say, for other purposes. And if the mixing valve is in close proximity to the hot water heater, even though the temperature of the water isn't the highest at the mixing valve, there will be some calcium that comes out of solution. So 3 months goes by, there's a little bit of calcium buildup on that shuttle mechanism that you showed, Kevin. And so when there's demand, it's locked in that position, and you're going to have too cool of water, and it's just not going to be stable, or maybe too warm water. And so that's where digital mixing valves, if you have hard water conditions that aren't solved by other means such as water softening and the like, is a really good solution. And this particular example is a case where a thermostatic mixing valve had hard water scaling problems and was replaced with a valve that actually exercises and is digital. So that was a really good point and a good question that one of the listeners had. There's another question. Let's see, we're after the hour. But as it relates to ASSE 1017, the question, Kevin, you showed a slide that talked about the maximum temperature variation that a valve needs to stay within based on flow rate, 3, 5, 7 degrees. Do you know, is it a test where the outlet temperature is measured and then the water temperature on the inlet and outlet is changed and variation is measured, or is the outlet temperature that you are the setting of the valve, say 120 degrees, you set it to 120 degrees, is a test that you're just measuring that the outlet temperature is within plus or minus 3 degrees of that? It's not a time-based test, it's basically accuracy-based test.
There is a period of time, they say, change the flow, reduce it by 50%, for example, and wait, I don't remember what it is, maybe 1 minute or 2 minutes, and then take the measurement. So there are some periods of time in there where they actually take that measurement and let the valve steady out.
Okay, very good. Back to digital mixing valves, you talked about different brands. Well, some brands might have an exercising feature, other brands of digital mixing valves, perhaps not. Is there a time of the day that is recommended for exercising? And if so, when is that, is the question.
Just in the middle of the night, sometime when there's generally little to no use, that's the best time to let the valve go through its stroke. The Legionella valve takes a couple of minutes because it's a 60-degree stroke, so it goes all the way one way, all the way back, and then back to where it was. So you don't really want to do that when you have high usage.
Okay, very good. Another question came in concerning when you're showing balancing, commercial recirculation balancing valves. In this case, the question was, does Caleffi's thermal balancing valves close off 100%?
Oh, the balancing valves. No, they have a minimum CV. If you remember that graph, there was a horizontal line near the bottom of the flow. The 116 has a minimum. You have to have that, or the thermal motor won't know what to do. You can never shut the water off completely. So there's always a little bit of a flow through there so the valve can react to temperature changes.
Another question came, another scale question. Are some products, thermostatic mixing valves, more susceptible to scale than others? I suppose that means brands. And I'll answer that. Yes, they are. It depends on the material used inside of the thermostatic mixing valves, because all things being equal, scale will precipitate out on surfaces at different rates. Polymers, as an example, are more resistant to scale accumulation than metals. So a valve that has a generous use of polymers versus metallic type moving mechanism inside of their valve will be more resistant to scale accumulation. And the Caleffi mixing valve has the shuttle mechanism is a polymer type design.
Mark, if I could add to that too, it's the temperature of the hot water has a big effect on how often the valve scales up too, because we know that the minerals precipitate out at the higher temperature. So if you're feeding a mixing valve 170 degrees on the hot port, there's a potential to get a lot more scaling than if it was seeing like 140 degrees or 150 degrees. And I forget what the factor is. I think it doubles for every 10 degrees or something like that, the scale precipitation. So usually when I see a valve that scales up quickly like this, this question here, within the first 90 days, they said they were seeing issues. It could be that the hot water, number one, you've got hard water, extremely hard water possibly, but also that they're running that tank at an elevated temperature too.
Another question, and probably Bob, you're best to answer this, is related to that. If you do have a problem with the thermostatic mixing valve with scale, is it recommended to just replace it, or can you clean it, or it depends?
Well, yeah, and this picture is a good place to be in. I can explain what I've done in a couple jobs, especially a job like this where it's a critical application. If you put 3 ball valves on all 3 sides of that and a little service port next to it, like a Webstone valve, for example, if some of your folks know the Webstone's got a ball valve shut off and it's got a little full port ball valve next to it, you could actually run a cleaner through that valve without taking it out of there. You could just, take the pressure off it, shut off all those 3 valves, and hook up your a delimer kit like you use for a tankless water heater. And usually it only takes about a half hour running that delimer acid through there that you can clean them out. If they're not plugged up completely where water's not going through them, then obviously probably gonna have to take it out and replace it and take it back to the shop and give it a good working over. But if you're gonna do a yearly maintenance on it, and you had those 3 isolation valves on that, just like you would do in a hydronic system to isolate a component, you could just get one of those little 5-gallon bucket kits, and comes with the cleaner and everything, and just delime that valve right in place. So that's another option for ongoing maintenance where you do have hard water conditions.
Okay, very good. Another question came in, and it might have been shared with the audience already, but it was relating to the growth of bacteria, which is, as we know, becoming more and more commonly communicated in the press and the media. The question is, does Legionella grow in water or on the pipes? For example, if the recirc water is always taken back to the heater, and heated back up to 140, would that sufficiently address bacteria concerns?
Like I mentioned earlier, it will look for somewhere to hide and feed. It has to feed off of something, so it's going to look for a place where it can stick to the wall of the pipe where there's some biofilm or corrosion or somewhere where it can hide. Now, if it goes back to the heater, yeah, it'll be killed as long as it stays in the 140-degree water for a half hour. But generally, it will proliferate in the layers of the piping. Thanks for letting us be with you for this last hour, and see you later.
Yeah, thanks everybody, and thanks to my team at Caleffi for putting it together. Thanks, Mary. See you on the next one.
Bye-bye.